This is Turbocharging AI/ML Workloads, revving up speed and resilience. I'm Lerna Ekmekcioglu. I'm a solutions engineer at Clockwork Systems. And prior to this, I was at AWS for about 3 years and before in large financial services companies, but always in New York. So I'm really excited for SREday in New York. Okay. All right. How many SREs here? Okay. How about application developers? Okay. Interesting. Anybody working on AI/ML? I see 2.5. All right, sounds good. So first, I want to start with the different layers of an AI/ML workload, just like a cake. I like cakes. So on top layer, we have the workload itself. In this case, I'm using an LLM model, and it is built upon frameworks and libraries such as DeepSpeed for optimization and PyTorch for deep learning. Typically, to train these models correctly, we need large amounts of data. And in order to speed up the training, we typically need to break up this data into mini batches so that each GPU works on part of this data and it creates its own partial results. And then at the end, they need to talk to each other so that they can synchronize the data. So they have, for example, full gradients as opposed to partial gradients. And to be able to do that, they need to speak to each other. And for that, they use collective operations, first of all, to do these synchronizations across the GPUs. And in terms of the libraries that they use, NVIDIA's Nickel is one of those collective communications libraries that enables inter-GPU communication. And at the bottom of this cake is the network card, which speaks InfiniBand or RoCE. It should be RDMA capable. Remote direct memory access is a key feature for fast data transfer between two nodes. You go from one node to another node's memory directly bypassing the kernel. In a traditional app, you would use Sockets API, and you would go through the networking stack of the operating system in the sender and the receiver. And this tend to be slow because you're using a lot of CPU processing time, CPU cycles. In an RDMA app, on the other hand, we're using RDMA verbs API, and we're bypassing the kernel. So we are actually not using as many CPU cycles. This enables fast data transfers. We're speaking to the network device directly from the app. And in terms of high throughput and low latency, the fabrics that we use is either typically RoCE v2 or InfiniBand. And I want to talk about a little bit about these two. In the upper layer of the stack, they're the same, but at the network and link layer, they differ. So at the network and link layer, InfiniBand uses proprietary InfiniBand network layer, InfiniBand link layer, and it requires proprietary hardware such as proprietary NICs and switches and cables. It tends to perform really well, but it is costly. In terms of RoCE uses UDP IP and Ethernet, which you already have in your data centers. It doesn't require any proprietary hardware, works with Ethernet hardware. That is RDMA capable NICs and lossless transmission support from switches required. It is comparable in terms of performance to InfiniBand, and it is less costly. So I want to talk about traditional networks versus AI networks next. Traditional networks to me are like the buses in the city. So we tend to expect delays, and because it's going to be packet drops and retransmissions, they're going to incur tail latencies to our applications. We expect best effort service. In AI networks, on the other hand, we have lossless fabrics, minimal delays, and we expect best performance. They're like the Formula One racetrack, for example. Traditional networks, the network card speeds go from anywhere up to 25 gigabits per second. And the safe link utilization rates, we tend to try to keep them at below 50%. We don't want to clog those pipes beyond that because then there's going to be more congestion, more delays. In AI networks, we tend to use cards that are 100 gigabits per second all the way to 800 gigabits per second. And the utilization rate for the links is typically at 95% or more because these training jobs are running all the time for months and months. The types of workloads that we have in traditional networks, we tend to have heterogeneous workloads. We have elephant apps, such as a Spark Data Shuffle job with chunky packets over the wire. And we can have mice apps, such as an e-commerce app that has teeny tiny packets over the wire. But the speed of one app does not directly impact the speed of another. And they're running over TCP, IP, and Ethernet networks typically. In AI networks, we have homogeneous workloads. They're tightly coupled. and they're running over Rocky or InfiniBand. So what I'm going to do next is dive deeper into these AI networks. So here is one run of one LLM training run. If you profile it, that it consists of cycles of compute followed by communicate for each and every iteration. In my head, this is like a relay race. So you have GPUs computing their partial results, just like a runner is running her own part of the track. And then the GPUs need to synchronize their results so that they all have the same data. And that's similar to the runner needs to pass the baton to the next runner and so forth safely so that they can all finish the race together. So this is what all-reduced compute communication cycle looks like, and this is using Nichols ring implementation. So here you have components of the sum that is getting passed around in the ring, and each of these worker nodes are going to add their values. And at the end, you have the total sum that gets passed around once more in the ring. So each and every worker node has the result. So the collective operation, this all-reduced operation's total finish time, is based on the sum of the ring latencies. If there's a slow worker node here, slow GPU, then that is going to determine the job speed. It's similar to a relay race. If you have a slow runner, that slow runner is going to basically determine the finish speed for the whole race for the team. And if you look at the total job completion time, 30% of it depends on this communicate phase. So I want to dive deeper into what goes over inside this wire. So I have two nodes here, typical nodes with 8 GPUs and 8 dual-ported NICs. So I have 16 logical NICs. GPUs generate messages. Messages get divided into chunks. Chunks are mapped to Q pairs. Q pairs are packetized. The data is packetized by the NICs over the wire, over InfiniBand or Rocky. And the receiving NIC is going to take this up the stack. And in terms of the topology themselves, what we see is typically a fat tree network. So you have the GPU nodes at the bottom. You have the top of rack switches, whether or not you have rail optimized design. You have the spine layer switches, and you have core layer switches. When we talk to the GPU cloud operators and their customers, we hear these are the top 3 networking challenges that they face. So the first one is lack of visibility, then lack of reliability, and congestion. So I want to go through each one of these and then talk about a solution for each, and then I'll have a demo at the end. And these networking challenges together, they lead to longer job completion time for AI/ML workloads. So this is an actual team that faced this issue where the top of rack switch has more than 3 down uplinks, and they only noticed it 6 months later, and they don't know why this happened. So teams are lacking the real-time insights into the connectivity between nodes, into the quality of these paths, not only at the network level, but also at the job level. They're unable to identify and resolve issues in a timely manner. So at Clockwork, basically what we do is we're out of Stanford University, and this is our paper, which is describing our clock synchronization algorithm. It is software-based. It is high precision, so sub-microsecond accuracy, and it measures one-way delays at a high degree of accuracy. So we have a productionized version of this. So what we do to gain visibility into the GPU cluster network, we create a NIC-to-NIC probe mesh. It's a lightweight probe mesh, but it gives us ability to monitor the health of the network, not only at the fleet level, but also at the workload level. So when you have applications running as well, you can see the quality of the paths and the delays on these paths. To do this, we synchronize the clocks of the NICs and the CPU with a common reference. And after that, we can take transmit timestamp at the sending NIC. We can take any ECN markings at the switches, and we take receive timestamp at the receiving NIC. And this way, we can measure the one-way delays accurately for each and every flow, each and every Q pair. In this way, you can isolate, is it the app or the network? Next is reliability. And this happens a lot in GPU clusters today. So if you have AI/ML jobs, then this is one of the reasons the jobs crash. Links, in this case, flapped more than 10 times within the past hour. And to fix this, they need to send technicians, actual physical people that have to go to the data center and swap out cables. So this leads to job crashes. And when jobs crash, you have to fall back to your previous checkpoint. And this could be one NIC out of the 16 in a node that flaps, that goes down, that takes down the whole job. So that's pretty significant. If you have a job that's been running for months and suddenly the job crashes and you haven't taken a checkpoint, that is bad. And the reason why this happens is because in a large enough cluster, you have large amounts of optical transceivers, and these optical transceivers overheat, or the dust particles cause these NICs and links to flap. So it's fairly common in a large enough cluster for this issue to happen. There's a very well-respected publication called Semi-Analysis that talks about this. So the link can flap in an interior link from top of rack switch to a core layer switch, or it can happen in an exterior link from a node to the top of rack switch in a rail optimized design where you have the NIC 0 of the node connected to port 0 of the switch, and that's how the node is sending data to all the other nodes. If this link flaps, then it's severe, the whole job crashes. So we detect this failure and we shift the bytes to an alternate path. And because we're monitoring the health of the paths, then as soon as that link recovers, we shift the byte back so that all the NICs are again carrying data. And I'm gonna demonstrate this. And the final one is contention. So you may have multiple flows contending at the spine layer links, and this results in congestion and a severe degradation of throughput. So here I have two senders. I have server 1 sending data to server 4, server 6 sending data to server 3. And these senders are not aware which of these paths are more or less congested. So I have light paths that are less congested, darker paths that are more congested. And because the senders are not aware, so they're putting 50% of the data on each of the links. And you can see the flows are contending for bandwidth at the spine layer up there. So what we do is like Google Maps or Waze. So we know which paths are congested because we know one-way delays accurately. So we shift traffic from congested paths to uncongested paths. And in this way, we eliminate congestion. To be able to know one-way delays accurately, you need clocks synchronized. So that's what we do first at the NIC level and the CPU clocks synchronized. And then we do the dynamic congestion load balancing. This is an Oracle Cloud. So on top, you have the all-to-all job. It's 100 gigabits per second throughput is what these NICs can do. The throughput is getting to 84 gigabits per second. And the one-way delays at the bottom actually show the reason why. So you have some of these flows are at the nanosecond range one-way delay, but a few of them are at 50 microsecond range. So that's very significant. Remember, slowest runner is taking down the whole team. So the slowest paths are really taking down the job speed. If I start a second all-to-all job, then you can see the jobs are really contending for bandwidth because you can see the one-way delays at the bottom shoot up to 100 to 150 microsecond range. And the throughput for both jobs is below 50%. And finally, when we turn the solution on, we minimize these one-way delays such that the throughput reaches closer to the theoretical max at 92 gigabits per second. That was a lot of information. So we'll look at the actual demo now. So here I have 4 nodes and we're in Oracle Cloud. So I have 4 and 5 in one rack, 6 and 7 in an adjacent rack. You can see all these logical NICs, 8 dual ported NICs, so 16 healthy green NICs. There's 8 GPUs in each node. This is the probe mesh. So within the same rack, the one-way delays between NIC 1 of node 4 and NIC 1 of node 5 is around 600 nanosecond range. And if I go across racks, then the one-way delays are around 1.5 microsecond range. And right now there's no workloads running. So there's no jobs running. This is just the fleet level metrics. So we have the probe mesh running and that's all. I'm gonna start an all reduced standard job. And you can see it up there between nodes 4 and 6. So first we'll see that node throughput goes up for nodes 4 and 6 to 1.47 terabits per second. So 1.5 is the theoretical maximum here. I have 100 gigabits per second NICs here. And I can see exactly what each NIC is doing in terms of throughput. They're doing about 90-ish gigabits per second. And if I click on the one-way delay again, now between these two nodes, 4 and 6, before it was 1.8, now it's 3.2 microseconds with the workload itself. Next, I'm going to do the NIC flapping experiment. So I'm going to flap one of these NICs. Just one out of 16 is going to go down. So you can see the job started getting marked gray because the job crashed. The throughput for the job went down. And the NIC is now gray because we detected that it is actually failed. If you look at the NIC level counters, all the NICs are no longer carrying workload data. You can see there's no significant traffic on those NICs anymore. So the job crashed, you have to fail back to a previous checkpoint. Just to prove that it's not going to come back, I bring back the NIC, and it's detected healthy now. The job itself is not coming back, so the job crashed. This is what happens in GPU clusters today. So if you have AI/ML workloads, you would have to fail back to a previous checkpoint. At best, you took it 30 minutes ago, so you lost 30 minutes of training. You will have to load all your training data, all your weights again into the GPUs and start over. And if I look at this NIC itself, I can see exactly when it crashed, when it flapped. You can see the probe traffic here, and you see the gap where the NIC flapped and the NIC came back, and the job is down still. So next I am going to start an all-reduce job with Clockwork plugin, and I'm going to repeat the same experiment. So first you can see the job again between nodes 4 and 6, and the throughput for the job is at 1.47 terabits per second for each node, 4 and 6. The NIC level counters are again showing for each of the 32 logical NICs about 90-ish gigabits per second. I will flap the NIC, and the NIC is going to be marked gray as it just did, so it's down. But because we have the remaining NICs, so and we know this NIC is down, NIC 1, so we are shifting the bytes to the remaining NICs. So they're picking up the slack from NIC 1. They're doing more work. That's why the throughput went down. You see the yellow line, that's NIC 1. And you see the remaining NICs that are now carrying also NIC 1's traffic. But the job didn't crash. It's still running. A little reduced throughput because we lost one tire in our tractor trailer. So I bring back the NIC. Because we're monitoring, so we know that the NIC is back. So the NIC is now marked healthy. And we shift back NIC 1's traffic to itself. So now we have all NICs up and running, and we recover the throughput back to what it used to be before flapping automatically. So it's at 1.47 terabits per second, and all the NICs are carrying data now. So it's self-healing itself against NIC flapping. I'm going to start another job. It's an all-to-all job. Again, it has Clockwork plugin. It's cross-rack jobs. So two cross-rack jobs, they're going to contend at the spine layer flows. So you can see the red NICs, those are the slow NICs. So there's some contention creeping up in the fabric, and the throughput for the first job went down from 1.4 terabit to 800 something gigabits per second. And the second job that I started can only make 600-ish gigabits per second. So they're making about 50% or less than what they could have made in this cluster. And you can see the NICs are now making about 50-ish gigabits per second each. And you can see why, because there's a big distribution for the one-way delays at the Q pair level. Some of these Q pairs are at like 3-4 microsecond range, and others are all the way up to 46 microsecond range. This big distribution, and you can see ECN marked probes, network telling us that there's congestion up to 18, 20 every second. The idea is the slowest flows determine your job speed. So our throughput right now is being determined by those really slow flows that are taking 50 microseconds. So I'm going to turn on control, which is this congestion-aware load balancing, to mitigate this. So because we know one-way delays accurately, we know which paths are more congested, which paths are less congested. So we're shifting the bytes from the more congested paths to less congested paths. And in doing so, we're recovering back to our original throughput for both of these jobs. We're using the network the most efficient as we can. So right now we're doing about 1.4 terabits per second for both jobs, and the NICs are again doing about 90 gigabits per second. And the reason for that, if you look at the one-way delays at the Q pair level, that we no longer have the giant distribution. We've minimized the one-way delays, and they're now converging to about 16 microsecond range. And the network also tells us now that there's less congestion because the ECM mark probes are much less, just a handful every second. And this is just to show that basically these two jobs are still doing 1.4 terabits per second. So my key takeaways are, if you have AI/ML workloads, then watch out for NIC and link flapping. This will result in job crashes. in large enough clusters. So you want to make sure you checkpoint so that you recover from these job crashes. And if you have basically slowest flows, right, in your jobs, they're going to determine the overall job throughput. So you want to maximize throughput. To be able to maximize throughput, you want to minimize your delays in your network. And thank you.